All right, hi everybody. This is an introduction to reliability growth. In the next hour, we'll be quickly going over what a reliability growth program is at a high level. So we'll start with the definition of reliability growth. And it's the systematic improvement in a reliability parameter caused by the successful correction of deficiencies in item design and manufacture. So what we're aiming to do is two specific things. There's two functions to this. The keys are we're looking to measure the reliability of the system, and we're looking to systematically improve it at the same time. Thus, the name reliability growth obviously makes a lot of sense there. So our objective is to create a team that covers all technical aspects of the product. We want to make sure we have representatives from the major disciplines. And this goes beyond just technical. There can be value in having somebody from legal there, somebody who's, works in a function in administration that may be able to provide some interesting perspective on the product. But this is one of the biggest values of reliability growth, is that as issues are occurring in tests and being analyzed, by having multiple disciplines looking at the issue right from the beginning, you're much more likely to get a better direction on where you want to drive to find root cause. If you have issues that come up that the assumption immediately is it's a mechanical issue and it's handed to the mechanical engineering team, obviously that's how they're going to approach the problem. And it won't be until they've gotten a good way through their analysis that they might conclude, you know what? I think this is electrical, or I think software might be a better place to start. And so this, in fact, is not a good use of time. Whereas if software and electrical and others were present when the issue was originally identified, they probably would have been able to contribute right then and say, do you know what? These symptoms are very indicative of X, Y, and Z that I've seen before. So by having a multidisciplinary team, we create much more efficient analysis. In addition to that, when root causes are brought back to the program, by having a multidisciplinary team review the root causes that are believed to be found and the corrections that are found, you're ensuring that you're having a really good consensus from many different perspectives that we do believe we really have identified root cause and we really have found the right solution. So that's why it's you want to be very careful of having a reliability growth program that even can start with a lot of people, end up dwindling down to a few core technical people. We want to really encourage a much broader audience. So we want to grow the confidence to a specified value. We want to have a goal. A goal is critical here, because without a goal, we can't figure out what kind of resource or if we're on a good enough path to hitting our goal reliability at product release. So we're going to systematically identify the interrupts and faults in the product, assign an owner to each, identify root cause, and then implement the solution. So systematic is an important word to include in this because we want to make sure we have a methodology, and we'll describe one methodology that's very commonly used, which is the Toshiro methodology for consistently root causing issues as well as documenting them, and also systematically handling the data and analyzing it in a specific format. Now, the owner is another very important point. So this is an owner of the individual issue that's being root caused. Now, because they're their owner, it doesn't mean they have to be the person to solve the problem on their own. They can simply function like a small mini project manager, for this root cause issue that is effectively its own little independent project. What this does is it ensures there's a single point of contact for the greater team to get updates on the issue, and it makes sure that issue is also being well represented with regard to if it needs a resource or what else needs to happen to keep it on schedule, not to mention even reporting updates with regard to action items associated to it. So having an owner for each individual issue is very important. And of course, this also further justifies you want a lot of people involved in this. And sometimes there's some pushback about the idea of having a lot of man hours with a lot of people, and that this resource is being taken away from other elements in the program. But that's not the case, because without a reliability growth program, the same resource would be going towards generating information, finding issues, root causing them, fixing them. It just would be in a much more disorganized format. So there's really no added burden to the program from a man-hour standpoint. We're just taking what would have occurred and doing it in a much more efficient way. So by identifying root cause and finding solutions and implementing, that's where the product improvement part is occurring, because remember the objectives were to improve and measure. So what obviously the most significant value from this is the fact that the product that you end up having at the end of this program is significantly better than the product you had at the beginning. And the product, so the product you're going to release is going to be mature. And without a reliability growth program, what happens is that maturing happens in the field. And that is a very painful process. You effectively are putting your reliability growth program on your customers to do, because your customers are running the product. They are observing issues, reporting them back to you. There's usually an owner internally to try to solve the issue. And this is all happening in a very inefficient way. It's happening in a way that obviously hurts your brand. It's happening in a way that is extremely slow and extremely expensive, because trying to identify and root cause issues that happen in the field is much harder than what happens if you do it within your own testing program. Obviously, there's the associated warranty cost. The list goes on, and I don't really have to describe it because pretty much every company on the planet has experienced those difficulties. So you are effectively bringing that process in-house. And instead of leaving your reliability growth program to your customers, where the maturing is happening in the field over multiple product generations, you're bringing it into your first product generation, and the efficiencies, cost effectiveness, and all the other peripheral issues, are greatly improved. So how do we do this? We want to run the system in a normal operating mode. And what I mean by normal is it's a use case we've agreed upon that we want to make the reliability statement on. So if you run the product in just its nominal, easygoing manner, when you're making these reliability confidence statements, which is effectively predicting the future, saying we are X amount statistically confident that we're going to hit X reliability goal in the field, that statement is no longer valid if the testing conditions don't match the field conditions you're making that statement on. So what we need to do is make a decision on the use case for the reliability growth program. So you don't want to take nominal, because then statistically half your customers are running it harder than you are, so the reliability statement is unlikely to be valid for them. So what's going to happen is when you release the product, what actually occurs in the field is not going to match what you measured in your program. So a common thing to do is, if you're not sure what you want to do, take what you think the 95th percentile of your customers, how they run it, and have that be your use case. And sometimes that's not even an exact use case like in the field. It can be a composite use case of different ways the product is used mixed together that wouldn't normally occur. And I call this my midlife crisis use case from a story I made about how you could create a use case of a user that is is really not represented in the normal use cases, but is a great way to have a composite. And and what I mean by not existing in real life is that your use cases aren't simply different degrees of increased stress in the set, whatever your set stress categories are. It's that maybe your product has an ocean use case and a desert use case and a mountain use case, and they have elements that don't cross over, but you choose to make an artificial use case that grabs all the elements you think are important from those three and combines it together, even though you'd never have ocean conditions on top of a mountain. But yet, you know that when you make a statement based on that use case, it's representative to capture about 95%, the 95th percentile of your users. So that's what's meant by normal mode here. We are going to log and interpret the failures, so it is obviously critical to make sure our data output for reliability growth is something that we can then take that data as an input and have information be the output, because the information is what we're going to make decisions on. And we'll talk a little bit about what those metrics would be, the types of information that would be. So we'll make sure that methodology is there and systematic. We're going to create Toshiro chart for each failure, and we'll go over what a Toshiro chart is. You can use any documentation method you like, but I found the Toshiro style to be extremely effective, efficient, and simple, both for the active reliability growth program as well as documenting the reliability growth program so that in the future, individuals can look back at what occurred, what actions were taken, what failures occurred, and how they were solved. So to some degree, this is serving also the purpose of not only helping this program, but working as lessons learned both for functionality and design, as well as the methods for creating a robust product, because you want to get as much derivative value as you can from your new, more robust design, which is a more robust version of your technology. So by ensuring that all that information isn't just lost in people's notebooks or PowerPoint presentations that are filed away where nobody will find them, you will be, through the Toshiro method, creating a very simple way to catalog and sort what occurred in the future. So like I said, we want an owner to each failure. Without the owner, any individual issue is not going to be well represented and can easily fall through the cracks, which we've all experienced as well in programs. And then we want a root cause analysis method. There's many out there, but what's important is that we select one and we stay consistent with it. So one of my favorites is 5 whys, and one of the reasons why I like 5 whys is because of its simplicity, and it's probably about the most intuitive way to root cause for a human, because any of us who have interacted with a 5-year-old knows that the way they discover and learn is by asking why. And when you give an answer, they ask another why. And when another answer, they ask why again. And that's effectively the core of the 5 why method. If you continue to take each answer and ask why that answer happened, you will drive down to a root cause that you can take action on. And the reason why it's called 5 whys, it's just to kind of give some sense of how deep to go. Obviously, we don't want to go to 20 whys where you'll end up, the final one will be the big bang, right? You've gone too far, you can't do anything with that. And you don't want to do 2 whys because that's probably too shallow to really take to really get a good root cause. So it doesn't have to be exactly 5, but it just kind of gives you an idea for the scale where usually actionable root causes are identified. So here's the infamous bathtub curve, and the bathtub curve shows up so much in reliability education material because it's a great foundation for discussing a lot of the fundamentals of reliability through a product's life. And this bathtub curve here is an exaggerated one. No real product would go through these phases with these that are this clear and consistent. But what we're doing here is helping demonstrate the major contributing factors to the reliability of the population through its life. So the bottom axis here is time, and the vertical axis is failure rate. And time is in the sense of the product's life. So for this, we are looking to plot if we made a large population of product, let's say you release 10,000 products over a 6-month period. And we are going to track the failure rate for those products through their life. And in the beginning, we are going to have a lot of failures that are driven by what we call infant mortality, which are effectively quality defects, manufacturing defects that show up early. And when we get through midlife, we have what we call the useful life failures, which we often characterize the behavior as random. And what the random means is that for a complex system with many different types of individual failure rates, when you put those all together, a lot of times, when they're all matched together, you end up with what is effectively a hazard rate where at any given point in time, a failure is just as likely as any other given point in time. And kind of a way to describe this is, I always think of it as like, if you were to take my voice and you were to plot it, right, and pretend it was a statistical distribution, there would be very specific characteristics to it. There would be inflections that you could identify, as mind volume changes, and it would not be a flat line. But if and let's say my voice is representative of a failure mode. If we're at a cocktail party and there's 30 people in the room and they all have different inflections and volume changes, what happens is a static noise when you put all these different types together that effectively just becomes a static decibel level. So you really could just take a decibel level and have that be representative of audio for that party instead of breaking out all the individual frequencies. And that might be the best thing to measure at a high level, because really when you get down to it for a party, decibel level is probably the most important characteristic. There's going to be a threshold in which the neighbors complain, and then a threshold above that where the cops get called. Or you may want to use it to try to diagnose what's going on at the party, right? If there's a set level, if there's a flat level and then it drops off, you might say, well, I guess that's when the food was served. So it's kind of like that, and that's why you can start off with the assumption that it is a flat, random failure rate during use life. Then what will occur is there'll be this third phase, which will be the wear out phase. And what the wear out phase is there are predictable failure modes that are degradation from a stress to a specific failure mode relationship that will begin to occur, and they will increase very rapidly. And this, of course, then dominates the population with regard to what's going on. And really, calling a wear-out failure a failure is not really a good description, because that's how a successful product's life ends. It's really not a failure, it's a design characteristic. It's a wear-out design characteristic as far as I'm concerned, because it can be predicted pretty accurately if you knew the exact stresses and variabilities around that one specific unit. And if everything went well, that's how it ends. So you can see that this makes it very easy to chop up the bathtub curve into 3 distinct data sets. And I've also included under here the individual types of failures in those dotted lines to show that the high-level bathtub curve is really a composite of those 3 contributing types of failures. And all of them are represented through the entire product life. They just have different degrees where they become dominant. Obviously, the quality failures are much more unlikely to contribute to failure rates later in life. They tend to show up earlier. Obviously, wear-out failures are not going to be a big contributor early in life, and the stress-related failures are always there. So when you put these 3 curves together, you get that traditional bathtub curve. So, reliability growth. How does reliability growth help us measure and make a better reliability that's represented in the bathtub curve? So, reliability growth aims at characterizing the behavior during useful life. So this is very important to keep in mind, because data points that we believe are associated to quality defects and data points that we believe are associated to wear out should not be included in the data set that we're using to make our confidence statements in reliability growth. So I'm going to say that again because it is so important. Failures that are associated to quality are not to be included. That means that as you're running your test units in reliability growth and you have a failure that you end up root causing is to a manufacturing defect, that failure will not be included in the data set used for making the reliability growth statements. It doesn't mean throughout the data it just goes to a different initiative, whatever initiative you're currently doing, to address and improve quality in the manufacturing process. But it's not to be included in the data set for the reliability growth. The same goes for wear out. If you have a unit that fails and you are able to root cause it as a wear out failure mode, which you would do by first, it should match the known wear out failure modes, when the product was designed that are expected. Car tire, that would be the tire tread wearing low. I mean, that is very clearly a degradation from a stress, during use life. That's very predictable. Usually a wear-out failure mode also has a metric you could follow that would give a prediction of when it's going to occur, because it is a degradation. It's not something that's working fine and then all of a sudden out of nowhere with no ability to indicate or to have monitored occurs. With the tire tread example, you could go at any point in its life and measure the progression of wear of the tire tread. And if you have the life curves for that wear out failure mode, you could even predict that, hey, we're halfway through life, which means that, we're going to fail at another 20,000 miles. So again, if you have a failure and you identify it as wear out, it should be removed from the data set that you're going to use for your reliability growth confidence statements. But again, don't throw them out. That's tremendously valuable information for your studies on wear out. Because remember, you can make a very reliable product, but if you don't understand when it wears out, you're going to still have catastrophic field issues, because what's going to occur is you're going to have large amounts of your population in the field failing all at once. And that's simply because the reliability of random failure is no longer dominating the behavior. The wear-out failures are now becoming the major contributor. So that's something very important to ensure that you're doing as well. So what we're looking to do is characterize and improve where this flat central part of the bathtub curve is. So we're going to have these, what we should see happen as we're doing this is we should, if we are tracking this, with the bathtub curve, we should be seeing it getting lower and lower and lower. And then obviously, in the programs with equality, what you would see is that vertical gray line that caps the first phase of infant mortality would be moving farther and farther left to where the quality failures are happening earlier and earlier. And you would also, of course, see the top of that side of the quality curve come down lower and lower to where it's a very small radius down at the bottom. You obviously would have a horrible manufacturing process if you started out with this extremely high failure rate that then you had to do a ton of testing before you could release any to the field. So our focus with reliability growth is characterizing and improving the midlife and the bathtub curve. Now the way we're going to show the data is not on the bathtub curve, because we want to be able to monitor our progress towards that goal of that flat line. So the way we typically show that with a complex electromechanical device is in a chart where on the bottom axis is not time of the product life. It's much more valuable to have time of your test program, because now you can align this with your actual program schedule. And you will have major milestones on there like first prototype, M3, manufacturing prototype, and actual product release, which of course is the most important one, because the y-axis is our statistical confidence in the product being able to do its reliability goal in the field. So we'll be making decisions throughout the program based on our confidence goals. And because the reliability growth is giving a trend, we can give status updates during the program. We're not just waiting till the end of the test to when we can make a statement about how the product's doing. That would not be very valuable. It'd be too late if it wasn't sufficient. But we can set goals that are that in the interim, that let's say for manufacturing proto, we would want seeing a 60% statistical confidence to know that at release we're going to have an 80% statistical confidence. And what that means is you'll have a conversation with leadership, project managers, and we'd set in advance we should be at 60%, and that's a very easy thing to communicate. And if at that point in our program we're actually at 40%, that should be triggering a discussion. What's going on? Why are we at 40% instead of 60%? This is concerning because it makes it very unlikely that we would get at 80% by release, which is what we want, and we're going to have our business decision be based on. So that conversation usually goes one of two ways. Why are we at 40%? Well, either A, you're having issues with the product, failures that you're not solving, and the product is truly performing, like representing itself to be very likely to not be able to perform to the goal of reliability. So that would then direct a conversation on, do we extend our product development program because we're having technical issues with the design we can't solve? Can we put more engineering resource on? What do we need to solve these issues? The other direction that conversation can go is, product's performing great. We're getting far less failures than we thought, and any we get, we solve quickly. We're just not getting a lot of test time. So if you want to have a higher confidence to make business decisions on, we need to invest more in the reliability growth program. We need to get more units on test. We need more test time. We need more resource. And that will then help the leadership make the decisions they need to make about resource, time to market, and the technology. So what does it mean to have statistical confidence in a reliability goal? Well, statistical confidence is not really so much a measure of the product as it is a measure of you and how well you understand your product. So you can, of course, do a reliability growth curve with many different types of metrics or styles or configurations. You could have it be a growth of MTBF, the mean time between failure. You could have it be a growth in the actual reliability percentage. But we have to keep in mind one of the big purposes of reliability growth is to not only improve the product, but measure it. But you're measuring it so you can communicate to the rest of the program where you're at. How good is the product? We're not just being left with leadership asking the R&D group, how are we doing? And they go, good, right? And you get to the next major milestone, how are we doing? They go, good. That's without, anything specific enough to have a conversation, because they also could say bad, and we want more resource, and leadership's gonna be like, you always want more. Why am I giving you more? You always want more. But instead, here we are with some real quantitative information to make that conversation meaningful and help people understand and make decisions about, well, it's okay, we've decided that time to market's so critical that we are okay releasing at a 60% confidence, because the reason we have a low confidence is we didn't have the unit's performing technically fine, we just haven't done enough testing, so we're going to take that risk. It's a much more specific conversation. So by having the vertical axis being confidence for a set reliability, so your reliability goal for your product, let's say, is 99%, what we're going to be watching grow is our confidence that a larger population would behave in the same way our test population does. So they use the word confidence because it does translate the meaning very well to the emotional definition of confidence. If I had just designed a new fusion-engined airplane, a technology that never existed, and I asked you if you wanted to ride in it, and you would say, well, how confident are you that this is safe? I'd be like, oh yeah, I tested one, it worked perfectly. Well, you can't test one of something and have confidence that the next one's going to work in the same manner. And then I say, okay, that's fine. I tested 3 of them. Let's throw your family on and go. And you're going to say you've tested 3 of them? I'm like, they work perfectly, right? So what if they worked perfectly? The odds that represents the population in the field is still very low. So the confidence grows statistically. We can make statistical transformations based on known distributions as you continue to log test hours with certain performance. And one of the more common ways to translate that is the chi-square distribution, and it works very well for doing that translation of the likelihood of a complex electromechanical device performing, a larger population performing in the field. And you're going to notice here that there's 3 lines on here, and we're going to talk about that next. Why we'd be tracking something called the virtual, something called actual, and comparing it to the goal and how those all are created. But first I wanted to show you that, as most of you know about me, I love my information graphics and ensuring that graphics can communicate information at multiple levels and are very tailored for the audience. So I showed you that very simple curve previously, but sometimes a reliability growth plot will look like this. And this is one I created as we continue to evolve and get closer and closer with leadership by sharing with them each week at their meetings. Based on the questions they were asking, we kept changing how we were presenting the information. And this really created a tremendous amount of efficiency and fluidity to what we are sharing and how quickly we could do it, and a tremendous amount of resolution when needed. So the first thing here is you'll see that red, blue, and green lines, and that represents the 3 lines you saw in the previous one where you had the goal and the 2 other lines. And in this case, the dotted green line is our goal. And you'll notice that this is in failure rate, so this is not percentage confidence growth. They wanted to know about failure rate was what we wanted to make decisions on. So as I said, you can choose any metrics you like, and statistical confidence wasn't as helpful for the audience. So we're looking for we set our goal we wanted for instrument failure rate based on program phase, and you can see it drops down. And then there was a big interest in the fact of we were doing simultaneously external testing programs and internal. So we had our internal reliability growth program, and externally we were running newer units at customer sites, basically in field trial programs that customers were very interested and willing to be a part of getting a chance to use this newer technology, this big jump in technology, and they were happy to be a part of improving it, and they had the opportunity to engage with it earlier, and also provide input on things they wanted different. So we had both of those generating data for reliability growth, but there was a lot of value in tracking those as two separate data sets. And some of those weren't just for value to the product. There was also the value to the program, our testing program. The difference at any given point in time between the blue and red, internal and external, indicates they should be the same, right? I mean, if they're different, something's different in the testing program, because they are very likely, of course you would check that it's the same products with the same changes, but maybe we're not using a good use case in-house, and we should reevaluate our use case if our use case that we're using, which is supposed to be representative of how the customer is using it, is giving very different results. So we've even included in here the opportunity to evaluate the testing protocol use case itself, and that was of interest and always of concern, that we weren't running our systems the same way the customer does. So that information can be extracted here. There also was interest in going down to specific customer sites, what was happening at individual points in time. So you can see we even added data points for specific customer sites, and those sites had specific revisions, or maybe they were operating the instrument differently. Now, the conversations often went into, very quickly, they wanted to know if there was issues slowing us down, what the issues were, and how many. So you can see here we have a list in the top right there, a key showing hard failures that occurred, the amount that were fixed and closed, what issues were still open and unresolved, and also 24-hour day runs, providing information on short runs like that. So you can see that you can add a great deal of complexity to the graphic, which is effectively the summation of the information you've created from the data and the interface of the reliability growth program to leadership, where the value really is. So let's take a little bit look at what the process is and why there's those three lines. So the goal line is what's created before the program starts. And this is what we believe the progression would be to get to our end goal. So in this case, we started off with the fact that we want to have an 80% statistical confidence by the time we get to, in this case, we wrote manufacturing prototype. Because after that, there was just going to be tuning to it with regard to manufacturing to reduce cost and also, ensure better, quality. So if that was our end goal, we needed to have the interim goals. And this curve is calculated using what's called the Duane Method. There's Duane, Crow, AMSA, which are ways to project or also measure the progression of product improvement. And when you do this, it's actually a log-log type relationship. So you can take the slope of that line and bring it to a table to see if you are on a slope to what degree of improvement. So when you start out, you can set your goal based on what you believe your investment is going to be. So what kind of return should we be getting on investment in our reliability growth program? And that would generate a curve like this. So we have our goal curve on there. So now what is this virtual and actual? So the actual is your actual data set. This is calculated using chi-square from the actual runtime that you're getting for your cumulative runtime for all your units and the actual failures that are occurring. So as you can see, it doesn't grow very much because there's a lot of failures occurring as the product is slowly improving. And those failures, those historical failures, hold down your average values. But when you think about it, that's not really what we want to be making business decisions on. Why would I want to make business decisions on a 3 revisions ago design? Because the failures that are included in that are from 3 revisions ago, and there's 7 different failures there that we've already fixed. And we know those failures we fixed are not going to be in the released product in the field. So that I want to make decisions based on what I believe is going to be in the field. So this actual data set, this actual statistical confidence that's measured from the full data set is not really very helpful. What is very helpful is what's called the virtual. And the virtual is what's our statistical confidence in the product's performance if we take out all the issues that we believe very confidently that we've resolved and are not going to occur in the released product. because that's what we're looking to do. We're looking to make a statistical confidence statement on what we think the released product will do. So as you can see, the virtual confidence will grow because effectively it's getting rid of the failures in the data set that have occurred and we've solved, allowing, releasing it of that burden. So at some point though, we may want to set a period where we prove to ourselves that all these fixes that we said should permanently eliminate those failures actually have. So you can set aside time, or even in a different test area, units that have all those fixes included and are going to be, should show a very rapid demonstration of that confidence growth, because those issues do not occur. And that's what this plot shows at a high level. Now, the way you get from the actual to the virtual is the Toshiro process, as I described, and we'll go into that next. And that process is effectively helping you identify the issues, log them, drive them to root cause using the 5 method, and then create corrective actions that you can implement. Are there any questions so far on what I've covered here? All right, there's also an opportunity to ask questions at the end. So the Toshiro process. So the objective of the Toshiro is to have a single page that captures the issue that occurred, the analysis, and the corrective action, to where it can be cataloged and viewed. And it's not, obviously, as a single page, not going to include everything that occurred, but it's going to give you the opportunity to get the overview and also know where to go to get further information. So we'll go through the major sections here, and you'll begin to see how the value that it offers this process. So we want to make sure that it's consistent, and we want to make sure that we are systematically identifying the root causes and the and documenting the corrective action. So you see here how, again, I've highlighted the word systematic. And this will ensure that we are continuously improving, the product, which obviously translates to the customer's experience in the field, which is our end objective. Our end metric is always, to some degree, money and customer satisfaction or customer safety. So we have to keep that in mind, because that might change. That is a directive that changes how you define use case, and what we're measuring and what we consider different types of failures. You might put different levels of severity to failures. So again, it's that end effect of the product's performance in the field that is driving all our decisions and how we set up our metrics. So like I said, there's many problem-solving techniques you can select. So if there's another one in your organization that you already are using, and everybody's educated and familiar with, it makes more sense to include that in your Toshiro. So I'm going to go through showing the 5 why, but there is nothing constraining you to that. So again, we want the cross-functional team of representatives when the Toshiro is created. This is important because they're going to be identifying what the issue is in a problem statement that makes sense to everybody. Problem statements and the way they're written can have obviously a tremendous effect on where the analysis goes. And also the owner of the Toshiro will be assigned at that point, and it's going to be one of the people who represents one of those different disciplines. So with regard to the frequency that the team's going to meet and create and review Toshiros, that's going to be up to the progression of the program. It might be every day, it might be twice a week, it might be once a week, but it should be at intervals that matches the progression you want to have happen of the issues being identified, root caused, and fixed. So one of the first things here is the ID number. Now the ID number is critical because when you catalog these and you want to be able to have a way to uniquely reference them. And this isn't just for after the program, this is during the program as well. Because you're going to be logging data with failures, and those failures should be able to have a reference to a Toshiro that addresses the failure. And that's why this number has to exist, be documented on the Toshiro, and be unique. And you might even have these Toshio numbers cross-referenced to other systems that you have that maybe catalog field failures or other types of failures in other tests. And you might in fact want to, in that system, refer to Toshio number 27 because it's the same type of failure you just saw in the field in your field root cause number, or it's the same type of failure you saw in a different test lab where you're doing a different test. So this ID number is very important and ensures the information is not only used better at the current time, it ensures you're always getting that continuing value because it'll be a part of your lessons learned. Number of occurrences. So number of occurrences and impact are listed here because they contribute to deciding which failures you want to address. I mean, very quickly we'll have a lot of failures and you're going to have to pick which ones to put resources towards. So if you have a failure that occurs 10 times versus one that occurs once, obviously you're going to get big bang for the buck in improving your MTBF reliability percentage or confidence by addressing the one that occurs 10 times because that pulls out 10 failure points over any specific period of runtime, as opposed to the one that's just a single one. Now, impact is the other factor. And impact, you can create a scale that is 1 to 5 or whatever fits that simply, obviously, if it's your 5 most critical, that could be, death or injury to the user or patient or, whoever your product affects, that is probably going to be what drives you to give that issue immediate attention versus something that's, when it fails is an inconvenience. Even if the inconvenience one occurs 10 times and the critical one occurs only once, depending on how you've done your scales, the fact that it occurred once will be irrelevant if it's something that's that severe. You're going to put your resources there. So number of occurrences and impact are to help you direct resources in the reliability growth program. Now, revision and date. I don't like to frequently up-rev Toshiros. They should, in the same Toshiro, show changes in the analysis and what's occurred and capture the full story. But sometimes a Toshiro, you're going to want to up-rev it and leave an older rev when there is a major redirection or splinters into more than one analyses, and it might even change into 2 different root cause analyses from the same symptom. You might find you have multiple. So that's when the revision can be helpful because you want to keep these Toshiros tied together, same ID number, but by having them be uniquely identified by a revision, they're still associated to each other. Having a date on here, it's just helpful from a historical standpoint that let's say that there was some disconnect in understanding where this Toshiro fit into a bigger program. The date might be the key that gets you to be like, oh yeah, that's when we were doing product, this product at this time in this revision, so that must have been associated to that program. So the owner, as I said, this is somebody who's effectively operating as a mini project manager. And in doing so, they are going to be the representative for the Toshiro. They're going to ensure that it's not lost and left to where it's forgotten about until a later date. They're going to ensure it's getting the resource it needs, and they're going to help follow up on action items to a lot of other people on the team who probably have a lot of different action items to make sure that it stays within their priority list as well. We have the problem description here, and it is extremely important that this description be complete and concise, and it states what's happened and doesn't begin to go into the why it's happened. And this can be hard to do. A lot of times when people write problem statements, you kind of accidentally begin to interject your thoughts on what happened, why it happened. And it takes a little bit of work to kind of keep it down just to the facts of what was observed. So that's something that everybody should be very willing to correct each other on if you feel that a problem description has gone beyond just the description. We have the 5 whys, and as I said, the 5 why methodology is effectively a chain of whys where the next why is directed at the previous answer, and we will end up with our final why if basically being the root cause. And a little test I do here to know that it is a good a good progression from the problem statement through the 5 whys to root cause is you should be able to read it backwards, and it tells a very clear story that this happened because of this, because of this, because of this, and then to the actual, and this is what occurred. So if you can read it backwards and there's not big jumps in logic and it follows along, it's a pretty well done process. A picture can be added, or chart, or something to help people who are not familiar with the technical details, related to this issue, be oriented. We have to remember that we very intentionally grabbed a very broadly, disciplined team, and some people might be very far removed from the technology and the issues we're talking about and the functionality. So something here to kind of help create some general orientation is a good idea. So the root cause will be listed here, and it's the most basic cause that you can take action on. And there should be a clear cause and effect relation between the root cause and the problem description. So it's good to stop and take a moment and make sure this is there. When you're super close to these analyses, it's very easy to miss having the documentation be clear for somebody who may be looking at it for the first time, far in the future, looking back to understand what was done. So taking these moments of reflection can be the difference between a tutorial that doesn't really do its job in documenting what's occurred and one that does a really great job of it. So the actions here, you'll see there's a label for type, which can be to correct or prevent. And the actions here, you list the action. There should be an owner to the action. So as I said, the tutorial owner is not the person who's going to do all the work. This is the owner of the action. So these can be the individuals that are doing the individual analysis and trying to get us closer to root cause. And with the ones that are the investigative ones, that should be marked. Those are the ones that we're doing during the 5Y. And then the final one is the corrective, and this is in response to the root cause. So the I's are in response to the 5Y's if you're using the 5Y method, and the C corrective ones are in response to the root cause. So we're also going to include the status, so that in the reliability growth meetings we can review where that action is at. We should have a due date set, when the action is given, to help us understand how to manage the resource and reliability growth. And then, of course, we would want to document the actual date that the action was completed. So that is what I wanted to share. It's a quick high level of reliability growth, and I would love to take your questions now.